Okay, so let's resume where we left off. All right, so to kind of recap, energy is always released during the formation of chemical bonds, and then what happens in when we break chemical bonds, that always requires an input of energy. Okay, so you may be asking, oh, but what happens if energy overall is absorbed, right? So sometimes in chemical reactions, sometimes the result you don't feel heat being released, right? You sometimes a beaker can feel cold. Well, that's the reason that is because the net effect is that it takes more energy to break bonds than the energy that it takes to break chemical bonds is higher than the energy required to form new chemical bonds. So that's why the net effect is a positive. What we say, that's where we get a net effect of energy being absorbed from the surroundings, and then that causes something to be cold. But we'll talk more about that when we talk about enthalpy, which is the heat of reaction when chemicals give off heat or absorb heat. Okay, but in general terms, we say energy is always released during the formation of chemical bonds, and then breaking chemical bonds will always require an input of energy. Or to break chemical bonds, we must absorb energy. A system must absorb energy to break the chemical bonds, because how can a chemical reaction take place if we don't provide energy to break the chemical bonds of the reactants? So if you kind of think about how chemical compounds get changed during chemical reaction, it's more logical to think that we break chemical bonds by putting in energy. So if we want atoms to kind of break apart, we need to put energy so they vibrate faster, and they vibrate out of that, and they break the force of attraction to be able to move and react with something else. Okay, so just think about, how do we get atoms to move further away from each other? By giving them energy, right? So the increase in kinetic energy and the increase in potential energy causes the atoms to move further apart, and thus this will make the bond longer and eventually breaking the bond. Okay, so let's look at these two examples right here. So the first example, this is ethanol, and this is ethyl. This is dimethyl ether. So you see in this compound here, the reaction is pretty much the same. They produce 2 moles of carbon dioxide and 3 moles of water, but one produces more energy. So when energy is on the product side, we say energy is being produced or evolved or released from these molecules. Okay, so even though ethanol and dimethyl ether, they produce the same amount of moles of products, you see the energy produced is different. So you could produce pretty much 52 more kilojoules of energy if we burn dimethyl ether. But the problem with dimethyl ether is it's a gas, whereas ethanol is a liquid, so it's easier to handle at room temperature. But dimethyl ether is a gas and is extremely volatile, so it's very hard to work with. Okay. So the difference in the energy content here is pretty much the strength of their bond. So we'll talk about bond strengths later on in this chapter, but the takeaway is that ethanol has a very strong OH bond, and you see here in dimethyl ether, all the hydrogens are bonded to carbon and not the oxygen. So there's no really strong polar bond, And that what makes the energy content higher. Thus, dimethyl ether is pretty much more reactive than ethanol because it releases more energy. Okay? So, one way to translate this is that ethanol has stronger bonds because it took more energy to break them. Thus, the energy released is less because, the energy of the bonds formed on the product side are the same. But we can conclude that it took more energy to break the bonds. So the energy released is going to be less because it required more energy to break the bonds in ethanol. So that's why the result is lower. So the more energy required to break a bond, the less energy you release as a product. So that's kind of how it works. So the more easy it is to break a bond, the more energy you're going to get out because the easier it is to break the bond, it means the molecule is unstable to the reaction conditions. So if you have stronger bonds, it's going to take more energy to break them. So making it harder for a reaction to occur with less energy, if that makes sense. Okay? Okay, so the key takeaway here, if you produce more energy, the bonds in the reactants are weaker. If it produces less energy, the bonds in the reactant are stronger. So that's the main takeaway here. So I'll highlight that. Okay. All right. So to summarize this, stronger bonds equal more stable, release more energy. Release less energy. Weaker bonds, less stable, release more energy. So when you're devising like energy processes, you kind of want to think about where you get that energy from. Like that's why we can't really use water to get energy. It requires a lot of energy input. We'll talk about why using water directly is not very favorable, but using the reverse process, forming water from gases is favorable. So that's why, in some, I think there, cars nowadays, they're thinking about using, hydrogen as a fuel because it's a very favorable process to mix with oxygen. To get water vapor, and then that associated energy that gets released can also power cars and stuff. So we really had to think about the feasibility of these compounds. Like it's not always a case where you just look at a compound and say, "Oh, okay, why not use this compound?" Well, you have to consider the practical effects, right? What are the byproducts? Excuse me. Let me get a sip of water here. So, you gotta think about all the practical aspects, the byproducts. Will water vapor damage the car? Well, pretty much in all combustion reactions, though, you do get water as a byproduct, so that shouldn't be a problem. But some things you have to think about are the starting materials. Is it realistic to produce the starting materials in large quantities for everyone to use as fuel? And you also have to think about how cheap it is to get. Like you wouldn't like combust a very expensive pharmaceutical drug to use as fuel, right? That's just out of the question. But in theory, like any hydrocarbon you take, or any pretty much organic compound, you could theoretically combust it and to get CO2, maybe an H2O. But you wouldn't want to use something with like sulfur or nitrogen because then you'll get SO2 gas and very toxic nitrogen dioxide gases. So we wouldn't want to use that. So that's what contributes to smog, right? NO2 or pretty much NOx. So a combination of nitrogen oxides. So it's just something to think about. But when we take in air, right? When we take in the air of our compounds. So when we take in air, sorry, lost my train of thought there. So when we take in air and put in oxygen into the vehicle, it really it's complicated because nitrogen also gets oxidized under extreme temperatures. So it's almost impossible to avoid getting nitrogen as a output or as a nitrogen byproduct, nitrogen oxide. So there's really some practical aspects to it as well. It's like, oh, can you reduce the amount of NO2 produced, etc. So these processes are more, when we're devising chemical processes, we really need the help of a chemical engineer to kind of, think of how we can optimize the process and make it more efficient, safer, and ultimately save more money and be much more environmentally friendly, so we're not polluting the air around us, right? Okay, so let's use this checkpoint here. So in the following reaction, okay, are bonds broken or are they made? So here we have two individual oxygen atoms, and they're combining to form O2 gas. So here we can say atoms. Oops. So atoms are combining to form a bond. So bonds are being made, right? So we could just circle bonds are being made because, they're coming together to form a bond, right? So will this reaction release energy or require an input of energy? So, like we said here, energy is always released during the formation of chemical bonds. So we're going to say it's going to release energy. The reaction will release energy. So I'll write it also here. Release energy because of bond formation. Okay? All right. Now let's talk about heat. What is heat? So you may think, oh, heat is just temperature. Well, that's not very good. That's not very quite right to put it like that. So heat is the transfer of energy. Okay. So when it's really hot, right? What you're feeling is thermal energy. So heat, energy given off by increasing temperature, right? So so when you have a heat wave, right, the blistering heat of the summer air is transferring energy to you, which got that energy from the sun, right? So heat is usually accompanied by a change in temperature, but they are not the same thing. So temperature is pretty much the average kinetic energy of your sample. So if something's cold, the kinetic energy of your sample is low. So, the stuff around you, the kinetic energy around you is low. That's why it's cold. But when things are really hot, like we, heat something, the kinetic energy of the molecules or of the matter that's absorbing the energy is really high. So that's why it feels hot. Because, that heat then transfers to you, and that feels really hot to the touch because your molecules in the molecules in your hand, are vibrating very rapidly, and that causes a transfer of energy, and your neurons interpret it as pain. Okay, so it all has to do with kinetic energy. They are not the same though. Heat is usually the transfer of energy, right? So, like, say you measure the temperature at at a certain period of time, right? You know, it'll be the average kinetic energy at that time point, right? But you know, the heat transfer depends on it really depends on you know, where it came from, right? So like, if you were 5 feet away from the stove, or like a few feet away, like maybe like less than a feet away from the stove, you know, the amount of heat you feel will be greater than, say, someone who's like 5 feet away from the stove, right? They won't feel the heat as much as you do, because heat is actually not a measure. It's not the measure of the kinetic energy, it's the transfer of the kinetic energy. So we classify heat as the transfer of energy. Okay, so when things so heat is kind of like a very conceptual topic to think about, an abstract topic to think about, because it's not actually a physical thing. Even though we perceive it as such, it's the transfer of energy. So basically, energy can be converted to different forms of energy. Heat is one of them, and that's the thermal energy that's lost, you know. And usually, heat is energy being transferred, and it can cause a raise in temperature. But temperature and heat are not the same thing. Okay, so we should get that cleared out of the way. So kinetic energy is referred to as the temperature is the measure of a substance's average kinetic energy, whereas heat is the transfer of said energy. Okay, so the amount of energy transferred to something can raise something's temperature, but you know, something's kinetic energy, it can't automatically be transferred to another substance's kinetic energy. For example, you know, you can't like say, okay, if I have this object at a certain temperature, if I place it to another object, I will now transfer all my kinetic energy to it. That's not true, right? So that's not what happens. Some energy is going to be transferred to the object you bring into contact with the hot object, but in reality, some of that energy is also going to be lost to heating the air around the object. So some of it gets lost as simply heat. That does not go into raising the kinetic energy of the cold object. Okay, so this chapter is really conceptual, so it's important that we kind of work our way through these concepts by thinking back to like more concrete examples. Okay, and we're going to do that a lot in this discussion here. Okay, so here's an example. When a hot brick is placed in contact with a cold brick, you know, like you have a brick wall, and you bring in contact some brick that you have in storage, which is much cooler. So energy will be transferred as heat from the hot brick to the cold one. Now, all that heat might be converted to or increasing kinetic energy, but some of it probably will not. Probably some will be lost, maybe to other sources of heat transfer, right? So the hot brick will get cooler, and the cool brick will get warmer until the two bricks, you know, are eventually the same temperature, right? So that's thermal equilibrium. So we can represent this change using the symbol Q for heat. So Q is the symbol for heat. So don't forget that. So Q is heat, not H. We don't use H for heat. We use Q. there's just so few many letters, and we need a lot of letters for variables here. Q is heat. H is not heat. H is something else. We'll talk more about that later on. What H means, what the symbol, or what the variable for H is. Okay. So we say here this negative sign. So we're going to use these negative signs conceptually here. So what this means is that heat from the hot brick is lost, so it's losing heat. So that's why we say it has a minus sign. So the heat lost by the brick is going to be absorbed. So there's going to be a positive Q, meaning heat is absorbed or energy is gained by the cold brick. So that's what that means. So if something has a negative Q value, that means it's getting cooler and it's releasing heat and transferring that energy to something else, which in this case, it's the cold brick. Okay? So in this case, the hot brick will have lost energy. The negative sign means heat was lost. And the cold brick will have gained energy. Okay? Okay. So when we think about how energy is transferred, we like to divide the universe into the system and the surroundings. Because we know, remember the first law of thermodynamics, energy in the universe is conserved or constant. So it's never changing. It's just being transferred to different forms of energy, right? So here we say the system I am interested in is this beaker, right? So here's my system. System I am interested in, right, is the beaker. So whatever is in the beaker, I'm interested in its energy. So what happens here is that what separates the system and the universe is this boundary, right? So in this case, we're usually working with chemical containers, beakers, vessels. So we say the beaker wall right here, or beaker wall, or the boundary is the boundary. Okay? And through this boundary, right, heat can be absorbed or lost. Heat can be absorbed or released. Okay, so it can be absorbed from the surroundings or released. So everything else, so this table, or air. So everything else. So everything else is the surroundings, or the universe is the surroundings. Okay, so everything else is the surroundings, so air, table, everything that's not the boundary of the beaker or the beaker itself inside is the surroundings. Okay. So here's a more detailed picture here. So here in our explanation here, see the boundary is the divider between our system and the surroundings. So what divides what's in our beaker between the beaker and the surroundings? That's the boundary. So that's going to be the walls of the beaker itself. And then if we're studying things under pressure, it's going to be the boundary is going to be the outline of our piston here, of our cylinder, and we have a piston pushing down. So we can then visualize our chemical system as having the thing we're interested in, the system, the boundary, and the surroundings. Okay. So since it's the last page, let's just go on here and just finish this discussion here. So we'll just have 3 videos for today, for this lecture. So let's go over these terms. System, the small portion of the universe that we are interested in. So usually our chemical system, chemical apparatus, chemical reaction. So it may consist of, water or other compound in the beaker, or gas trapped in the piston and a cylinder if we're studying gases. But when we talk about heat transfer, the system will be our main focus. So we care about what's happening in our system, right? Surroundings is everything else that's not the system. So it could be the atmosphere around us, what's outside of the cylinder, so the rest of the universe. So when heat enters a system, we say the heat produces an increase in the kinetic energy, right? So when we heat something, right, things get hot because the kinetic energy is increasing. The average motion of the particles is increasing in our system. So overall, the energy of the system increases, and then we say heat is transferred from the surroundings to the system. Okay? So when heat leaves the system, the particles get cooler, have a decrease in the average kinetic energy, so the energy decreases. So we say heat is lost to the surroundings from the system. So this is where Q system is negative, and then when heat enters a system, Q of the system is positive. Okay? All right, so last kind of concept question here. So use the motion of the particles to explain what happens to the particles of a gas in a balloon when heat enters the balloon from the surroundings. Okay, so let's just draw our little picture here of a balloon. So I'm just going to put some dots here that represent gas particles at a certain temperature, okay? So let's say this is room temp. Let's just say this is 20 degrees Celsius. Okay, so now if we increase the temperature to, I don't know, 60 degrees. Okay, so what's going to happen to the balloon, right? So assuming, balloons, the boundary is expandable, right? So the balloon's going to expand when we heat it, right? Because the gas particles will now have more kinetic energy, and when they have more kinetic energy, they're going to have more collisions with the walls of the balloon. And since the balloon's wall is elastic or expandable, the balloon is going to increase to a higher volume. So what we get is, so what happens is, well, that's not actually a good picture. Let me redraw that. Man, I don't think I'll be a good public speaker because I lose my voice really quickly when I talk too much. Okay. So you get a bigger balloon, right? So the gas particles are going to be moving, faster here. So I'm just going to say, okay, they're moving faster. Give them some speed lines here. Speed lines, speed lines, speed lines, speed lines. But it kind of looks like more particles. But just imagine that what happens is when this increases, velocity of the gases. So the velocity of the gases increase, right? All right. So when this happens, collisions with wall will increase. Okay. And with more force. So one thing to note is that the pressure is going to stay the same, right? Because as the speed increases, the volume of the gas, the volume of the gas increases, right? So we're also going to say volume. So the volume of balloon increases. But what's important is that at higher temperature, right, the velocity of the gas particles will increase. That will then turn collisions with the wall will increase and with more force. So what happens here is that pressure will remain constant. So that's why the balloon doesn't like pop right away, is because the volume is elastic. The balloon is elastic, so it can expand, right? Pressure volume of balloon will increase because the balloon is elastic, right? So let's just write here balloon's wall is elastic. So just like, you know, if you have a movable piston, the volume can increase. And when that happens, you have an increase in temperature, your pressure is increasing. If your volume can also increase, the pressure is going to remain constant, because as your volume increases, the pressure will also maintain a constant pressure. Will be constant, okay? So the particles, so the velocity of the gases increase, so we can also say that there is increased kinetic energy. Increased kinetic energy. And that's because, you know, with increased kinetic energy, we also have increased motions of the gas, and that's the result of the gases having higher velocity. Okay? So that's what happens. So let's just move this temperature here over here. There we go. Okay, so that'll be for this lecture. So that's our introduction to energy. So we'll taking these concepts now and talking about go more in depth mathematically with how energy is transferred from a system and how it gets its energy from the surroundings. Okay, so next time we'll talk more about thermochemistry, and then terms like enthalpy, internal energy, total energy of the system, how to relate it to a system at constant volume and constant pressure. Okay, so I'll see everyone in the next video. See ya.